Is going to talk to us about instrumentation and flight software systems.
All right, can you hear me? Yep. All right. My name is Ray Caperoon. I'm with a small company, Space Ground System Solutions. We do most of our work at the Naval Research Laboratory's Naval Center for Space Technology. I also want to acknowledge a couple other people who got some help for us who couldn't make it today, Mike Tietz and Eric Bradley from the Naval Research Laboratory, and Brian Davis from our company as well. And all right, I'll skip past the long-winded abstract here. So just wanted to kind of cover some of the experiences we've had with instrumentation over the last 20 years. At NRL, we've supported about 8 missions with this, with some of these techniques. So some of these things have been evolving over that time period. So what we're talking about with instrumentation is providing a time-ordered history of what's happening in a system while preserving the real-time aspects of that system. We can use these techniques to analyze system performance, such as contributions to latency, jitter, estimate worst-case performance when we have tight margins, validating any kind of estimates that are provided by performance models, and creating requirements verification evidence. You can also use a great deal of instrumentation help with diagnosing complex system issues, which is usually how our instrumentation got in there in the first place. So you can use that to test issues where you have a test configuration that you may not be able to support with a traditional debugger. You may have interactions that a traditional debugger may not reveal. And if you have non-deterministic problems that require real-time execution, some debuggers won't allow that. So what kind of things have we instrumented? We've instrumented all kinds of things from top to bottom. Operating system scheduling constructs such as semaphores, task context switch, sleeps, interrupts, those type of things. We have a infrastructure framework at NRL that we use that's very similar to the CFE CFS that provides exclusive data access, message passing, event flags, telemetry collection, all that kind of thing is instrumented. And then application events, state changes that are specific to your application or higher level code, errors, or even debug watch points when you're trying to track down an issue. We've used instrumentation at all phases through the development and operations of our system. So during development and integration, you have debugging, driver development, and some initial performance analysis. During our system and integrated system testing, we do final performance analysis and requirement verification and evidence. As we get to the integrated things, we've actually used the instrumentation to do on-orbit anomaly resolution. We build it in early, we fly it. Since we're going to fly it, we test it that way, and instrumentation is just part of our infrastructure. So this is a simplified kind of layer cake diagram, kind of show you some of those things. At the top level, one of these is, top level, you can tailor your instrumentation based on what your needs are. Here's where we talked about the infrastructure, where you have a CFE. Our 2 infrastructures are called RFA or RESP. That you can do those kind of things. You have operating system instrumentation if you can get in there that captures any kind of hidden activities. Maybe you have a semaphore or a interrupt lockout that you're not aware of in your operating system, and those can kind of get in there. That can be challenging unless the operating system provides capability of that. And if you're down there doing board support package development, you can get in there. So much like those cooking shows, when you cook a layer cake, it never comes out the way it looks. So this is kind of our package of layers. So we put our instrumentation right in here. It's a common layer of instrumentation with a number of backends based on what our applications are. Our infrastructure, RFA, works on that. It has hooks down into the board support package, straight to the hardware and through the operating system. So for instance, in the VxWorks projects we use the task swap hook to instrument our context switches. As a backend, we've used WinView for our backend to collect the instrumentation for us and then be pulled into the nice WinView GUI tools that they provide. Board support package, we've instrumented interrupt lockout routines to help track things down. And then I'll go into this a little bit more. We use backplane backend, instrumentation backends for capturing the data. And segue into here. So talk about the backends. We provide a common instrumentation interface that all of the different applications or infrastructure components can call. And we have, we've used different backends, a kind of a memory-based ring library with timestamps and a memory buffer. This is something that we use on orbit, since if the memory can be allocated there, the data capture is limited by the amount of memory you have, and it can be slow to download. We use on the ground testing, if you have a memory bus like a PCI or VME backplane we've used in the past, we've written the data out to those things to let the analyzers capture that data. That can be useful to get longer captures of data. It also gives you an independent timestamp capability, and also can interleave your instrumentation with backplane traffic when you're trying to develop custom device drivers that talk over the backplane. And over here we show we've used WinView as a backend that interleaves the operating system instrumentation that may be provided, and you can use the tools that they provide to do your visualization. So without these visualization analysis tools, you can generate a lot of instrumentation data that goes nowhere. So we've focused on 3 different types of tools to support, since our instrumentation libraries and instrumentation data is common across programs. We've generated a set of general purpose reporting tools to create just a human readable report. I'll have some examples of that coming up later in the presentation. Then we do some general purpose analysis tools. Again, these are usable from project to project. They kind of give you your analyses that you're going to do all the time. What's your task by task CPU utilization? What kind of interrupt processing times you might are you doing, or lockout times? And then we generate special purpose analysis tools for particular pieces of information that you may need for a particular program. Maybe you have a latency requirement. You're going to utilize the instrumentation data for verification evidence of that latency requirement. You can put together an analysis tool that kind of pulls that data out for you. Here's just kind of our typical reporting tool architecture. No big deal here, but you can show that we get the raw instrumentation data from whatever backend you've collected it to. We combine that information with our databases to kind of turn the IDs and little bit patterns into human readable information. And then you get your instrumentation that's time ordered with a little bit further information. And then these filters can be used to generate your generalized instrumentation reports and your special purpose reports there. And again, I'll have some examples of that coming up right about now. So this is just allegedly a human readable data output, but you can see here we have the raw times and raw data that came out of the memory buffer. These are converted to relative times from the beginning of the run. And then as the processing file goes through here, it can take a look at each of these things. And you have this one here is a context switch. We have a background diagnostic task being swapped out for a time manager in. So as the analysis tool can run through here, it can start to kind of keep track of your state of your system to tell you which task you're in or if you're processing a particular interrupt. So we have lots of things. These are our kind of task signaling event flags. When we go into when we swap out a task, we record the stack pointer program counter of that task, so we can even kind of do a limited traceback of where the tasks are being swapped. And you kind of have some information about an interrupt here. This is a red 750 trace, so you have a miscellaneous timer 3 coming in and coming out. So we'll go through some more details and put some more context into these. So these are just some of our experiences and where we've gotten the most bang for the buck out of this instrumentation. During driver development, so we generate a large number of custom hardware for our in-house custom developed hardware for our missions. A lot of it sitting on PCI or other backplanes. So In development of that, you want the ability to capture free-running, time-ordered interaction between the hardware and software that the single-step debugger can't always do. So in addition to that, you can combine that instrumentation with the hardware register accesses using some sort of bus analyzer to capture your hardware-software interaction. So you can see, while I'm in this interrupt, what kind of registers I'm reading, how did the hardware respond in that interrupt. Maybe that's kind of tracked down while you're having the problems you had. Is it a hardware issue because it's new hardware? Is it a software issue to get after that? So for this, we instrument hardware register accesses, interrupt entry, interrupt lockouts, and application-defined data watch points to kind of trace your execution flow. And this is just some kind of same trace as before, just with some of the details here. This guy here was actually, you need the context to know this, but this is our decrementer interrupt firing off an event. Is kind of where your interrupts enter and exit. You can kind of look over here at times to calculate or determine an interrupt processing time, and so forth. So after you get everything developed for your hardware and you got your drivers working, you're going to pull everything together in integration test, and again, especially useful with custom hardware. And very similar set of tools and experiences to the driver development in the previous slide. Kind of where we start getting into some other interesting areas using the instrumentation. As you're pulling all these things together, we've used the instrumentation to identify events leading up to fatal flight software errors or watchdog resets. I'm going to go into a little bit information about this later, but we record these things into memory. We take a watchdog reset or unexpected error. We have a method of preserving that memory, pulling all that down, and then we can trace into that. Is it a hardware fault, or was it a software fault? You know, we've gone as far as track down to things. We had a card with a flaky power generator, and we were able to kind of recognize some signatures of that and point ourselves to the hardware there. Usually it's software, though. And again, this also allows you to get some debugging into configurations where you don't necessarily have your JTAG type debuggers available to you. At NRL, this is where we start to use these tools to build up our experience, make sure we have the tools and procedures that we need to start working on on-orbit anomaly resolution type uses of the data. And here, what we instrument, anything we need to get the job done there. Another big use of the instrumentation data we've had was performance analysis. We've used this for both system tuning and requirements verification for various programs. So let me give some examples of requirements verification. We have some detailed analysis for context switch data to validate the CPU utilization telemetry. So we have just a telemetry point that says, oh, you're using 64% of the CPU or 33. How do you know that's right? We can pull this instrumentation data down and use that to verify that. So then moving down the road, we can just use that simple telemetry item to check our requirements. Or if the program requires, we can go into a little more in-depth look at the CPU utilization. We often have interrupt latency requirements that we write against our flight software. So from event to actuation is a common requirement to look at. So we had a system where we had a tight ACS thruster firing latency to run down. So we use the instrumentation data to run that analysis and run that through some tools to show that we did in fact meet our requirements for doing those things in the system. A lot of the data that we use for this performance analysis, task context switch, interrupt entry, interrupt lockouts, any sort of task scheduling flags and application watch points. And again, here's just where some of the hits are there. Same kind of thing we showed before. Now, I talked earlier about some of the more, instead of a human-readable report, just some of the analysis things. So this is just an example of a run we did. We had about 1.4 million entries in our ring that represented 45 seconds of data. And in that run, that gave you the CPU utilization for each of those tasks at a pretty high fidelity. Now, these are the task utilization after interrupt. In this particular system, the interrupts were pretty heavy on us, so we're using 7.6% of the system processing interrupts. So this is the CPU after that. We'll get back to this high interrupt usage in a couple slides. The other thing that here's another example of a report, a mutex utilization analysis, to kind of show what our different interrupts or semaphore usages are. So we can run the analysis and say, hey, anyone who has an interrupt lockout of greater than 1 millisecond, let's flag those and start tracking those down. So you get a report here of the different interrupt locks. These are the violators, and these are the kind of things that would show mutex 3 exceeded the limit at that particular time. So not only do you just say that guy exceeded it, then you can go back to the long form report and say what were the events that were, why was that a problem there. So, and these are reports that represent our early runs of before we do our performance tuning. So this is kind of our starting point to figure out where we need to make our improvements. And then with interrupt, so to get back to the interrupt, this is kind of an interrupt report with minimum, maximum, mean execution times, along with this kind of pseudo jitter number with the minimum instantaneous rate, maximum, and average execution rate. So this top guy here was a 400 hertz time tick interrupt. But you can kind of see that you had these very high jitter rates for these instantaneous calculations. So we use this information to re-architect our interrupt structure because in the RAD 750 interrupt prioritization scheme we were using, this guy would get preempted by another interrupt. So we figured we could move this 400 hertz interrupt over to the decrementer and get a lot better jitter performance on that. Another area of performance analysis is risk assessment and model validation. We did a lot of this on a recent program. We had a fairly high CPU utilization in some mission modes that we exceeded a 70% utilization. Our customers wanted a little closer look at that, and it was event-driven priority systems, but priority scheduled systems. So there was some uncertainty that we could meet our performance within margin. So we used this instrumentation to get a detailed behavior analysis to look at response times for individual events that were supporting that mission mode. And we had a de facto. So some of the events were asynchronous. We had de facto periodic scheduling by these periodic timers, and we would look at the maximum durations of 100% utilization windows to see how jittery our utilization was. And then we took some of this data and fed it into the CPA compositional performance analysis tool to validate. We use this to generate a worst-case model prediction from this tool, and use the instrumentation data to validate and correlate to that. So we could show that the cases we were running and collecting data were the predicted worst cases by the CPA tool, and kind of got the confidence that when we were in these high utilization, we weren't missing an important case there, and when we kind of snuck into the 80% utilization, we weren't getting ourselves into trouble. We were going to recover from that. You can kind of see here, this is kind of what that data looked like. So we were switching modes into the active mode, and we were sure that we were coming back to these different performance, CPU performance levels when we changed our modes through things. So you can kind of see how things were jittery, but no bad trends or anything there. And then finally, as we get onto orbit, we have a lot of experience using the instrumentation for anomaly resolution. We leave the instrumentation enabled for integration and test and on-orbit operations. So we've been able to diagnose these errors and quickly drive to root cause. We instrument everything we can think of and everything we can afford at that point. And some anomalies, we had a anomaly during integration tests where we lost communication to the spacecraft controller, and by forcing a watchdog reset, we've got a post-mortem instrumentation from that and determined that our tasks were no longer running at the expected priority, and that kind of uncovered a deficiency in the OS when chaining priority inheritance actions. That if you did that twice in a row, it left the low priority task at the wrong priority. And that also showed that our application was using the mutexes improperly that kind of led us to that situation in the first place, so we're able to fix that. And then here's an example of an on-orbit anomaly investigation. We would experience some watchdog resets on orbit, and with this system we had there, we were able to acquire the last 7 seconds of execution with post-mortem memory dumps. And then it showed that a critical task wasn't receiving an interrupt, which led to the watchdog. And after collecting enough data and patching it together over a number of resets, we're able to isolate the problem to a particular piece of hardware. And at least we weren't able to fix it, but we were able to understand the situation that we were in. There's a few practical considerations to keep in mind here. Instrumentation can add significant overhead. We've kind of baked it in, so we just kind of, since you turn it on early, you never know that it's turned on and off. But it can lead there. In fact, we've selected which sort of instrumentation to include to kind of scale it back. Some cases we've estimated our instrumentation is probably costing us about 5% of the CPU off the top. Instrumentation may not be scalable. Our initial implementations ran on an older 20 megahertz processor with a simple write-through cache. When we moved, and that gave us about 5 seconds of data in a 1 megabyte ring buffer. When we moved up to Red 750, the performance was greater. We were able to rip through all those instrumentation statements a lot faster. It took us about 4 megabytes of ring buffer to record the same 5 seconds worth of data. It really wasn't adding a lot of value. So at that point, we filtered out some of our instrumentation while writing to get a better set of instrumentation. To kind of talk about down here, when you're instrumenting a ring buffer on board, consider some capabilities, some buffer management to be able to stop on full or override on full depending on your modes. Adding filters can extend the period of time that can be stored in an online buffer, and that becomes important when you're trying to run down a particular value and you need a longer run of data. You can turn off the stuff you don't think you're interested in. Triggers are very useful for tracking down errors, so you can, when you hit a certain situation that doesn't result in some other larger action, you can turn the instrumentation off to preserve your data, or a trigger can start the instrumentation. And again, the post-mortem availability of the data is important for diagnosing those critical resets. It usually it provides requirements to your startup ROM to preserve that memory. Some usage considerations of when to collect the data. We've gotten into a habit of implementing instrumentation early and capturing data for each flight software build to kind of determine some sort of baseline behavior, so we can kind of look back and say, hey, when did that little thing start running faster, and try to trace behavior to changes in the software during our builds. We also collect instrumentation during formal testing to spot check any unintended activity. And we collect the data after any unexpected reboot. We make this part of our test procedures, and those turn into mission rules for the operators. And one final thing to kind of keep in mind, is kind of hit us in the past, is changes in flight software can change the meaning of the instrumentation data. Your command telemetry databases may change, which if you're instrumenting a command ID or a telemetry ID down there, you got to make sure you have the CM processes in place to be able to recreate those things if you want to go back and look at those. So kind of in conclusion, you know, our typical developments include evolving requirements, large numbers of newly developed hardware, and short schedules. So the event-driven priority scheduled systems are good for us, and we so as a result, we have a lot of non-determinism to do the formal performance analyses that we need to do sometimes. And this instrumentation also leads to expedient diagnosis of issues during INT. If you need to sell that to a program manager, there's your little hook. We've been able to turn around post-mortem dumps in minutes or hours after collecting that data during a TVAC, and that saves a good deal of money. You don't want to be putting the instrumentation data into the software during the TVAC. So instrumentation provides support for all levels of development, from development through performance tuning all the way up to on orbit. So our recommendation: instrument early, instrument often, and instrument like you fly. So, any questions or comments?
Over here, Stephen.
Yeah, I know of at least 3 NASA missions where the instrumentation was necessary to add after the fact to try to find the problem, and that became a configuration and management nightmare just to make changes to the software at the time of the test, and it went on and on and on. This brings up a question that isn't necessarily for you, Ray, but on that high-performance processor presentation that we saw earlier, how much are we supporting the data that you want to maintain over one boot to the next boot? Is that in that high-performance requirement as to how much you can use for post-mortem after a reset? Because that goes to the reboot, and I don't remember any requirements for that on that previous presentation.
Yeah, as far as I think the post-mortem data that we collect is probably going to be very mission specific, but I think the hooks and the hardware and the software are there. You know, the ARM core site debug and analysis tools are there.
Well, I'm looking for
and
what kind of PROM have we got on there that's going to survive storing the data between one reset and the next? Is it got to be electrically, you know, that kind of issue?
There's MRAM available for that kind of stuff. It's whether we put the service in there. It may be in the middleware service.
Okay.
yeah, so we're definitely going to have to think about that.
One of the things we did on the Cygnus mission, we did use MRAM for that, and we just had a sort of a circular diagnostic buffer that was just always writing some diagnostic information there, and then in the event of a fault, then it would lock that buffer. Okay, we got time for one more question, and then we need to move on.
So I'm just curious, a nice presentation. Do you know if tools that, I mean, I think of, Splunk for like system logs for computer diagnostics, and like Wireshark is a good tool for like USB and wireless and Ethernet and all that diagnostics. Have you any recommendations for open tools that for collecting this level of diagnostic information?
Yeah, we haven't looked at those too much. We have actually run into a couple interesting places that we wanted to investigate that actually came from kind of security forensics tools for combining a lot of event data with your system logs and memory maps and things like that. And I have a note somewhere that I should probably publish that somewhere. But that's the only one that we've used is just the WinView tool there. So, okay. Right. Thanks a lot.